Good morning, everyone. I would like to thank the Cholangiocarcinoma Foundation for supporting our research and, of course, for the opportunity to present this research. I'd like to thank all of our patients for serving as the motivation for us to conduct this research. The title of my talk this morning is Therapeutic Targeting of Fibroblast Growth Factor Receptors in YAP-Driven Cholangiocarcinoma. And Dr. Gores has mentored me throughout my fellowship, and he continues to mentor me, and he mentored me on this project. So as you all know, cholangiocarcinoma is a highly lethal neoplasm with limited treatment options, confounded by our poor understanding of CCA biology. This is a disease that often arises in the perihilar region, which you can see depicted on the MRI on your top right, and has a dense desmoplastic stroma, which you can see in the bottom photomicrograph. And although a variety of oncogenic signaling pathways have been implicated in the genesis of CCA, and we've heard about quite a few of them thus far this morning, two pathways have garnered attention of late, the oncogenic Hippo signaling pathway and the FGFR pathway. However, the interplay between these two signaling pathways remains to be elucidated. So as we've heard this morning, FGFR2 gene fusions are present in approximately 15% of CCAs. And YES-associated protein, or YAP, is a critical component of the oncogenic Hippo signaling pathway. YAP nuclear expression indicating YAP activation has been reported in over 50% of CCAs. And at Mayo Clinic, we have a break-apart FISH assay for the detection of FGFR2 gene fusions, and we found that these fusions tend to be YAP positive. So we were particularly interested in the potential interplay between these two pathways. Hence, we generated the hypothesis that FGFR signaling activates YAP. In this hypothesis, FGFR would lead to YAP activation, nuclear translocation, and induction of target genes, including potentially FGFR2. To address our hypothesis, we generated 3 questions. And our first question was, does FGFR inhibition result in YAP inactivation? To address this question, we employed the CCA cell lines KMCH and KMBC. We treated them with BGJ398, and we've heard a great deal about the efficacy of BGJ398 in the clinical realm. And with this work, we just want to show you what we found about BGJ398 at the bench. YAP activation was assessed by YAP nuclear localization utilizing immunofluorescence. And what we found is that BGJ398 resulted in a marked decrease in YAP nuclear localization, indicating that FGFR signaling may impact YAP. To your left are immunofluorescence images of YAP, DAPI, and the merged images. And to your right is the quantification of YAP-positive nuclei. Please note the significant reduction in nuclear YAP with BGJ398 in both the KMCH and KMBC cell lines. Phosphorylation of YAP at serine 127 leads to its proteasomal degradation. The kinase module, which is present upstream of YAP, under basal conditions, phosphorylates and inactivates YAP. So we hypothesized that FGFR would interfere with this, leading to YAP activation and nuclear translocation. Consequently, FGFR inhibition would accomplish the reverse, namely YAP phosphorylation and cytoplasmic retention. So we postulated that BGJ398 inactivates YAP by YAP phosphorylation. And indeed, what we found was that phospho-YAP 127, which was hardly detectable under basal conditions, was readily detected when these cell lines were incubated with BGJ398. And the second blot that you see is that of total YAP. The reduction in total YAP with BGJ398 treatment would be consistent with YAP phosphorylation and proteasomal degradation, leading to its cellular depletion. So having demonstrated that YAP activates FGFRs, we next sought to ask the converse question: does YAP induce expression of FGFRs? And to address this, we again employed the KMCH and KMBC cell lines and knocked down YAP using an shRNA approach, which you can see there in those two blots. And we assessed YAP binding to a transcription factor using immunoprecipitation studies and YAP localization to a promoter region by chromatin immunoprecipitation assay or CHIP assay. And we found that FGFRs are indeed upregulated in human CCA in a YAP-dependent manner. On the top here, you can see increased expression of FGFR 1, 2, and 4 in our CCA cell lines. Please note that the expression of FGFR 3 was negligible. And next, we knocked down YAP using an shRNA approach, and we found a significant reduction in the expression of FGFR 1, 2, and 4 in both the KMCH and KMBC cell lines. So our next step was to determine whether FGFRs were indeed a target gene for YAP activation. We conducted in silico analysis and identified binding sites for TBX5 in the promoter regions of FGFR 1, 2, and 4. Please note that TBX5 is a known YAP binding transcription factor. We were able to identify YAP binding to TBX5 using immunoprecipitation studies, and we also detected YAP binding to a promoter to a protein complex in the promoter region of FGFR 1, 2, and 4 using CHIP assay for these TBX5 binding sites. So in summary, these data are consistent with the interpretation that FGFR signaling presumably inhibits the kinase module, leading to YAP co-activation of TBX5 binding sites, which in turn induces FGFR expression in a perpetual oncogenic signaling pathway. So for our final question, we asked what was the consequence of disrupting this pathway. And to address this question, we employed a patient-derived xenograft model, and we've heard about these models in CCA this morning. So in these models, human cancers or tumors are implanted into NOD-SCID mice. And we had multiple PDX tumors, and not all were YAP positive, so we exploited that finding to see if BGJ398 had an effect only in the YAP positive tumors or whether it also had an effect on the YAP negative tumors. And once the tumors reached a size of 1 centimeter, they were treated with either vehicle or BGJ398 for a period of 2 weeks, and all mice were sacrificed at the end of treatment. And what we found was that the BGJ398 tumors had a significant reduction in nuclear YAP. This is immunofluorescence staining for a YAP positive PDX. And CK19 staining was utilized to detect the CCA cells. And on the top, you can see that there was abundant nuclear YAP in the vehicle-treated tumors. However, the expression of nuclear YAP in the BGJ398 YAP positive tumors was negligible. And we found that BGJ398 reduces tumor burden in our PDX model of CCA. So the BGJ398 treated tumors had a significant reduction in the tumor weights in the YAP positive PDX. In contrast, in the YAP negative PDX, there was no difference in the tumor weights between the vehicle and the BGJ398 groups. And in the YAP positive PDX, we noted areas of cell death and necrosis with BGJ398 treatment, and whereas no such areas were present in the BGJ398 treated YAP negative PDX. So in summary, we've identified an autocrine loop between the FGFR signaling and oncogenic Hippo signaling pathways in this loop, FGFR signaling leads to YAP activation, which in turn induces expression of FGFRs. And if this loop is inhibited by an FGFR inhibitor, there is YAP inactivation, cell death, and reduction in tumor regression. So these data indicate to us that FGFR inhibition holds significant promise in CCA, and that's something that we've already heard a great deal about this morning. But they also indicate that YAP may serve as a biomarker to identify patients who may have response to FGFR inhibition. Currently, we're investigating how does FGFR inhibition cause cell death. And our preliminary data suggests that this form of cell death is necrotic, and we think that has potentially significant implications because we know that necrotic cell death is more immunogenic, and necrosis can potentially bypass apoptotic resistance pathways, which are pervasive in CCA. Thank you for your attention.